Welcome to Telemetry Workshop. We have Mike Beacon from Low Power Radio Solutions. Whereabouts is it in Swindon?
Whitney.
Oh, Whitney.
Yeah.
Oh, Whitney. All right. Okay. So the structure of today. I'll plug my thing in.
Wow.
Okay. Right. So this is the session introduction. What we're going to do is have a bit of theory and then a bit of discussion and eating, and then there's some practical work in the afternoon. The theory basically just it's supposed to be a general introduction to low power radio, with the context being telemetry rather than broadcast or voice or anything like that. So Michael will give us an overview on low power radio. Gary was going to give us a quick intro into XBs and Bluetooth Low Energy. Then Richard and I will go through the HAD project. So there's a project we're doing with Mattel and Warner's and radio spares with high altitude balloons. So Richard will do an intro, then I'll go over some of the components and also try and demonstrate some of them. And then Richard will go through the details of the flight computer he's designed. Then there's some other telemetry requirements we have rather than just the balloon. There's the rocketry that Matt is working on, so it may be worth having a quick discussion on how the requirements may be different with the rocketry. And the other discussion we have to have is about antenna, okay? Because these balloons go far away and we need to be able to track them. We're using radios which are only about 10 milliwatts, so the aerials need to be very efficient. And then hopefully in the afternoon we'll do some practical work with some cheapest chips, 2.4 gigahertz radios and Arduino. Okay, right. Right, so I'll hand over to Mike.
No problem.
So that's back, that's forward.
Gotcha.
You don't need that one, and that one's a laser pointer.
Oh right, okay. Okay guys, this is a very, very interesting sort of place. Right, I'm going to give a bit of a chat about just generally low power radios. I'm not an expert on balloon telemetry and things, but I was speaking to Dave Akerman a couple of weeks ago in connection with the RLab project. Had a very interesting conversation. It's fairly advanced stuff. Right, so a little bit about me. I at the moment work for a company called LPRS, Low Power Radio Solutions, and they've been around for about 25 years. And I was one of the founder members of that, and at that time we were distributors for the radiometrics modules, which I think is one of the favourites for the balloon project. And then after a couple of years we started designing and manufacturing our own modules, which is what we do to this day. I've since left the company and about 2 years ago went back and I sort of work as a consultant. Right. My interest in this comes from, I suppose, my early maker days and things. Like I suppose most of the people here and things, I was always a tinkerer, a maker, taking things to pieces and putting them back together again. Then when I was about 8 or 9, got interested in model radio control planes. And so I started building my own radios and, using valves of all sorts of things. So that sort of interest has sort of gone through my working life. Anyway. The low power radio module industry comes about from about the 1980s when the government liberalised the radio bands. Until that time, most radio devices you had to have a licence for them. And what actually happened, they were forced into that situation because of the car key fobs that came along. And these were operating on 315 megs, 303, any frequency at all. So they thought it was about time that we sorted this out. And so they allocated a number of bands. And at that time it was the 418 megahertz band. Since that time, and also prior to that, there have always been a number of specific bands that have been available, ranging from sort of low frequency, tens of kilohertz for RFID, right up to gigahertz. These are generally quite small slots, and there's always terms and conditions required for their use. So the main term and condition is that the device that you use has been approved in some way. Now, at one time the radio agency used to be very hot on that, but just in this last few years they seem to have given up. It doesn't trouble me greatly, as these devices are fairly low power and they don't cause interference, they don't cause jumbo jets to fall out of the sky. So that's one of the key things, is they're generally low power, between 1 and 10 milliwatts. And that's got a number of advantages. It means they're local devices, and multiple devices can coexist. Various sort of schemes we have for coexistence. And generally these things are designed for short messages, tens of bytes to hundreds of bytes, not for streaming data. I've illustrated there some XV modules, some cheap and cheerful little ASK modules, and some easy radio modules as well. The guy that founded Radiometrics told me many years ago, he said, you have to think of wireless as being statistical communication. And I think that's a really good description, which I think in layman's terms means sometimes it doesn't work. So we have to make... Sorry,
a few more for the course. There he goes.
This way, this way. Round here.
So, wireless being statistical communication. So, as a user, we have to make every effort to make it more reliable. And if I have the choice, always I'll choose a piece of wire. It works so much better. What sort of things can we do to make it better? First of all, I think it's worth illustrating something what I call push and pray. If you go to B&Q, you can buy a cheap little radio fob and plug top things you can plug lights into. And those use very, very cheap radio. Press the button. And what's useful about it is usually the device is in the same room, so you can see that something's happening. But if it doesn't, you just press it again. So that's one way of doing it, and that's a simplex communication system. The biggest improvement we can make is to make it into a duplex or half duplex system, so we can have some confirmation that the signals that we have sent have actually been received. And with the advent of low-cost RFICs, that's the usual way of doing things these days. Although, sort of one-way communication still is used for simple remote control type applications. Thought it'd do a little bit of theory, just so you got a bit of a sort of understanding of how these radios work. Because later on, when we look at the balloon telemetry, there's some clever stuff that people are doing. But let's look at sort of the basics. The easiest, when you have a radio carrier, in order to convey information, you have to modulate the carrier in some way. There are many ways of doing this, but the schemes that are used for low power radio are sort of basically these three schemes. There's our digital data, and the easiest way to do it is just to switch the carrier on and off. So that's very much like the old Morse code transmitters and things. We're going beep, 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 beep. That works fine, and you can have very simple transmitters and receivers. You can make a transmitter out of one transistor and a SAW resonator, and a receiver, a super regen receiver, which is enormously wide, one transistor and an op-amp. Very easy to do. Disadvantage is when the carrier is switched off, the receiver's wide open to interference. So a slightly improved method is what they call amplitude shift key, where instead of switching the carrier completely off, it's just sent to a reduced level. That's got some sort of benefit, so it keeps the receiver quiet. These days, though, the most common modulation scheme is frequency modulation, where we take the carrier and we just shift its frequency slightly. And there's two modes of operation for FSK, frequency shift key, and that is either narrow band or wide band. cheap and cheerful RF modules deviate the carrier by tens of kilohertz, typically in the sort of 433 megahertz band. And narrowband modulation, which we're going to be looking at for the balloon application, is generally a few kilohertz. So we have issues then about initial frequency accuracy and stability. Okay. So dependent on the modulation scheme that we're using, we have receivers of different bandwidths. And I like to think of bandwidth as the amount of radio spectrum that you're listening to. So for a wideband receiver, you're listening to, as I said, tens of kilohertz, and that's quite nice because the accuracy of the transmitter, as long as it's within the passband of the receiver, you'll find it. But when we move to a narrowband system, you have to have much more accurate frequency control of both the receiving frequency and the transmit frequency as well. And that's certainly a challenge for the balloon telemetry. Along with this bandwidth, we then have, just because of laws of physics and things, of modulation indexes, narrowband systems will tend to be slow data rates between 1 and 5 kilobits per second, whereas wideband systems, you can go up to about 500 kilobits per second and still stay within the bands. Okay. How to implement a transmitter using a radio module is particularly easy. The modules are usually equipped with a number of pins, a power pin, a transmit data pin, sometimes an enable pin. So all we actually need to do is then hook some sort of encoding device up into it, and that may be, say, monitoring temperature with a thermistor, or button presses, or anything at all. Wakes up and it sends some data, and that's very, very simple to implement. And for simple encoding schemes, there's a number of ICs available. I pointed out here, these are Holtec HT12s, and those are cheap as chips ICs. You can buy them for 20, 30 odd pence. Hook them up to a radio module and make a very simple remote control system. And what they do is they provide a data stream that consists of 8 bits of address and 4 bits of data, or various combinations of that. And because it's so simple, and they use pulse width modulation to encode the ones and zeros. This particular scheme here uses it divides the bit into 3 bit times, so it's either 1 bit low, 2 bits high, or 2 bits high and 1 bit low. And they're very, very easy devices to use. And in order to provide some both security and also better reliability, what they generally do is they send the code multiple times. So you press your button and you're sending that same message 30, 40, 50 odd times. And the receiver is just looking at that, and it's looking for 4 consecutive messages that are the same. So that actually provides a reasonable amount of reliability. So that's a simple sort of encoding and decoding scheme. This bit of the slide, this bit of the presentation is probably the most interesting bit, because it will give you an understanding of how these receivers work and the sort of things that you need to do to get data through them. And here is the actual receiver circuitry. That can be either ASK or FSK, it doesn't really matter much, but somewhere in that block there is a recovered modulation signal here, which is generally, they may call it an audio output. And that audio output is actually quite a little useful diagnostic tool, because if you hook either some headphones or some speakers to it, you can actually listen to what the receiver is hearing. And that's always particularly useful. But the key thing I want to talk about is this little building block within the receiver itself, which is called the data slicer. And understanding of how this works will help you understand how to get data through radios. So the data slicer consists of an op-amp configured as a comparator. So are we familiar with comparators, how they work? We have 2 inputs, one we'll say at a fixed level, and then we have, if the other input's above it, the output will be high. If it's below it, it will be low. So it's just comparing the voltages. And in this particular configuration, what it does is it compares the average voltage determined by an RC network with the instantaneous voltage. So what we see if we were looking at that recovered audio output with a scope would be this. We would see digital white noise appearing out of it, just due to the amplification of the receiver. So digital white noise, and out of that digital white noise appears our signal. And the usual way to do it is to first of all send a preamble, which is just an alternating 1-0 sequence. And what that is doing is actually setting up the data slicer here. It's going to average those ones and zeros to set the DC level on that input at the average voltage. So it's sort of setting the slicing level in the middle of the digital data. Then comes sort of clever bits where we have to say, well, I now want to send what they call a sync character. And the sync character allows you to find the bit edges and then follows on the data. So this comparator, this data slicing circuit, has some unfortunate characteristics in that when we look at the digital signal that's coming out here, we'll see that digital white noise squared up, and we'll see the preamble, and then we'll be looking for the sync signal, and then we'll then get data coming out of it. And the difficult bit in designing a receiver is, or no, not in designing a receiver, designing a protocol, is to find that sync signal and to synchronize on the bit edges so we can start clocking in data.
If you've got too much data, does the average change, and will that affect it?
Yes, yes. And another snag I've shown here, what this sort of system won't tolerate is long sequences of ones or zeros.
Right.
Because if we send a long zero, the slicing level will slowly creep down, and it will creep down into the noise that's on that signal. So it won't work. The other thing that occurs is we get pulse width jitter as well. So our nice clean signals that we're expecting have got jitter on the edges. So the decoder has got to accommodate that jitter. So if it doesn't matter, but if you've just got an understanding of that, it's useful because you'll know how to decode data and, more importantly, how to encode data.
That explains one of the notes on the 2.4 gigahertz radios, where
Yes.
What they say is when you pick your addresses, avoid single bit transitions. So I guess because the address is the first part of the message,
Yes.
if you've got single bit transition, it's going to effectively degrade into the average level.
Right. Yes.
Okay.
Yes. And also the actual data encoding scheme. I said it won't tolerate long sequences of ones and zeros. So the usual way of encoding data is to use something like Manchester encoding. Are we familiar with this? Yes, everyone? Manchester coding translates a 1 to be, say, a 1 followed by a 0, and a 0 to be a 0 followed by a 1. And it's a nice encoding scheme. It's self-clocking because there's always edges. The average DC level is 0, and it's the general way to do it. Okay. When LPRS first started selling the radiometrics modules and its own modules, we had great difficulty with this because people, what they wanted to do was they wanted to hook it up to a UART. So they get a microprocessor UART, hook that up to the transmitter at the other end, take the receiver output and put that into the UART. It just won't work. Serial data UARTs have no noise tolerance at all, and it just won't work. But it took a long time to explain to people the sort of things that they had to do. So people then came up with smart RF modules. And generally with a smart RF module, you've got a built-in microprocessor that's doing the encoding of the transmitted data, and it's doing the decoding of the received data. And a good example is our LPRS, the Easy Radio modules. Those have just simply got serial data in on the transmitter, serial data out on the receiver. And they'll take up to 250 bytes of data, packetize it, do all the clever stuff, and then get it across the radio link. And there's quite a lot of these smart RF modules around. the general discussion is people say, well, you've got a microprocessor there, can I use your microprocessor? And they say, well, no, because one of the things is this is a very, very time-intensive task. All the time, you're monitoring bit by bit and making decisions on, what's happening. So the microprocessor is kept busy. A new breed of modules has come about in this last few years, which I call half smart, and these are things like the Hope RF modules. They are smart, but they're a bit difficult to drive. They have to have an external processor to drive them. And what you need to do is to be able to understand all the registers and why you're poking data into those registers.
So do you mean the RFM12?
The RFM12, the 22B.
I've got an example. So.
Right. These are very, very cheap. The RF performance is commendable. And I do notice that one of the balloon people has been using them.
They use the 22, I think.
They use the RFM22, which is a bit of a better device. They do need a lot of understanding. You need to know exactly what you're doing and why you're poking data into certain registers and how to configure them. But there's lots of third-party Arduino libraries available that eases the pain, as it were. Just generally some sort of hints and tips about how to use these modules. You must bear in mind these are very, very sensitive receivers, and they sort of care a little bit about the environment in which they live. So the general sort of thing, you want a fairly clean power supply. You want to put some decoupling close to the pins, the power supply pins of the modules. And it's quite nice to use a combination of a relatively large capacitor, say 100 M, and a 47 puff or something or other. It's got much lower inductance and does much better filtering of RF on its pins and things. Something to bear in mind is the local environment of where the receiver is that if you've got clock oscillators, say from a microprocessor, a switching power supply, something like that, or even fast logic, this will generate edges which have got harmonics that extend up into the UHF regions, and so it will tend to desensitize them. So you want to take care with that about where these modules actually live. Hints and tips on antennas. There's nothing better than a simple length of wire. These areas are all resonant, so it's got to be a certain length, but it's very convenient for these UHF modules, because at 433 megahertz, it's about a 6-inch piece of wire. 868, 3-inch piece of wire. Very, very easy to accommodate. But despite this, over my years, I've seen people do all sorts of things. They put them on top of batteries, they've wound them up, they've done all sorts of weird and wonderful things. Antennas like to be in free space. So there's literally free space around them. And the other thing that they like is they need a ground plane to work against. And again, Graham Sharp, as it was, from Radiometrics, gave me a very good analogy a few years ago. And he said, think about a ruler. And if you've got a ruler, you hold it in your hand, you try and ping it. It just won't ping at all. But he said, if you clamp it to the edge of a desk and you ping it, it just pings nicely. So I try and use that analogy because that's the ground plane against which it's working. If you're going to do your own encoding schemes, then you need to use a bit balance coding scheme like Manchester, and the most difficult bit is a clever sync detection and data extraction. The other thing you've got to contend with is that data stream may have noise spikes in it as well, so you've got to try your best to eliminate those. And something I say to everybody is always do real range tests. It's so easy to sit on the bench and think, yeah, it works. Go out, take it in, at a field, go and try it. And if you make modifications, change things, go and try it again. It's tedious, but you will be surprised. It's worth investing that time. It's also a bit of fun sometimes. When we started 20 odd years ago, there was, I think Radiometrics were probably the pioneers of these radio modules, because what they'd seen was they could actually get a radio module itself type approved, and then they could pass that type approval on to the user. Previous to that, if you designed a product with an RF in it, you had to take it to the test house and have it fully approved. It cost tens of thousands of pounds. So in the early days, I think Radiometrics were probably the pioneers of actually the radio module business. But since then, there have been many others that have come along. RF Solutions is worth having a look at. They do mainly remote control systems. They also do some modules. Have a look at the offerings we've got, and then there's dozens of them that I could speak. SparkFun do these cheap and cheerful ASK modules, the push and pray ones. Wouldn't really recommend those for serious sort of use. And Hope RF. There's also some very interesting chip suppliers as well. One of the ones that I particularly like are the Silicon Labs devices, which are used in the Hope RF modules. The RFM22 has got quite a nice device in there.
I've had a very good experience with this one.
Oh, have you?
Like
Yeah.
Cell Labs, yeah.
And the later ones, the 44, whatever it is, are really, really nice. Another one that I've come across is Axon, which is I think it's a German company, and they do some very nice devices. Very, very low power consumption as well. So anyway, you can find lots of them on the internet.
Just one. If you use a chip, though, you'd have to go for the type approval, would you, or not?
Yes. The idea behind the modules is that they come with a type approval. But if you're using a chip, in theory, you're supposed to go for a type. Depends what you're doing. If you're doing it as a hobby, I don't think anyone's going to notice.
Right.
But if you're going to do it commercially, then they're supposed to be type approved.
Even for the ISM bands.
Yes. Yes.
So
And
any emitter bands.
that's an interesting question, because you look at the RFO module, the Hope RF modules, and it says meets approval requirements, but it doesn't say they're actually approved. Look at the radiometrics devices; all of them have been type approved. So, for commercial applications, that's what you need to go for. The radio agency, which is supposed to police these things, I think has lost interest. I mean, the government doesn't want to fund it, so I don't know of any prosecutions at all that have been done recently, even by people using these things commercially. But it's not, as I said before, it's not a massive problem. These are tiny power outputs, a milliwatt, 10 milliwatts. You've gone 200 meters and then vanished into the noise.
I was going to say, where is there an actual problem to be solved by requiring this type of approval?
The problem that was solved was that it was a good way for the government to raise money and things, because it was also good for test houses, I think. If you take a product on for testing and things, the radio type approvals 2, 3, 4 grand. It also deters competition in the market. But from a technical point of view, what's the problem?
Yeah, how is it different from CE testing for like EMC compliance and stuff like that? Is it the same thing? Or is it different?
No, it's different. It's different. It's more stringent, and it's difficult as well. It's not much fun at all doing it. It's sweat-inducing, I can tell you. Just a quick slide there on the poor man's protocol analyzer. What I've done is I've sometimes hacked products and things and find out what protocol they're using. And quite an easy way to do it is to use that's something Audacity. And what I've done is taken that audio output and fed it into Audacity, recorded a signal stream, and then the other thing that you can actually do is then play that back again. So if you're trying to decode this data and you've got a microprocessor there, rather than just have a short burst of data, you can keep replaying that burst of data. So that's quite a good technique. And you can see there a bit of joy and fun that I've had working. First of all, I've been working out the bit times, and then I've been saying, there's the preamble, there's the sync character, and there's the data. Very often with the data, they actually go and encrypt it as well, which makes it even more difficult. Okay. Right, I'm not an expert on balloon telemetry, but as I said, I've spoken to Dave Akerman, and I learned quite a bit from him. The original plan was LPRS was going to give some modules to this project and things. The difficulty is that RS don't stock the radiometrics modules, no. So they wanted to use ours. We've got some very nice Japanese narrowband modules, absolutely beautiful, very expensive, but very, very nice. Not entirely suitable. They are narrowband and they look as though they'll do the same job, but they won't, for quite interesting reasons. Looking at the Radiometrics NTX2, which is what everybody seems to use. There are some good reasons why people use it. It's got what they call a temperature compensated crystal oscillator in it. which copes with the wide temperature range. I saw a slide earlier and things. It goes from what are the temperature ranges we've got
Up to minus 50 or something?
minus 50.
Well, minus 40.
Minus 40.
So if we use a simple radio module, it'll be drifting all over the place. And one of the difficulties is we're going to use the narrowest band receiver we can possibly make, because what we want to do is eliminate noise. The narrower the band of the receiver, the less noise you hear. So we want very, very narrow band, which then means we want the transmitter to be spot in the middle. So with temperature drift, the transmitter will be way over here and way over there. That's nice because it uses this temperature compensated crystal oscillator. And the other key thing that they've done is the modulation input, the data input, is, although it looks like a digital input, what it's actually doing is controlling a varicap diode within the device. So that means you can use that to trim the frequency. And I believe what they do using the NTX2 is they just get a DC voltage on the digital input and they're waggling it up and down to make a deviation of a few hundred hertz. Yes, is that?
Yeah, I think
About 500 hertz.
500 hertz, is it?
Yes, about 500 hertz.
Yeah.
On a standard, digital narrowband module, it's actually a digital input, so the frequency will shift 2.5 kilohertz that way and 2.5 kilohertz the other way. So you've got a 5 kilohertz deviation. Using the NTX2, you can have very narrow band operation in conjunction with a software-defined radio. Yes, I think is what they tend to use, in which you can then determine the actual bandwidth. So, the tough stuff for your job is frequency accuracy and stability over a very wide temperature range. I noticed on one of your slides as you were going through, there are limitations on the transmit power, yes? And also regions as well in which you can transmit and...
Well, so the regions dictate the ISMs that are available, the ISM bands.
Right.
So here in Europe it's the 434 and 868.
Yeah.
And in the US I think 915?
915. Weird rules in the US and things.
Right.
FCC is, very, very difficult to get through. They really want to discourage anyone else making radio modules and making radio products in general. So FCC is particularly difficult approvals and things. But it's generally about 10 milliwatts.
10 milliwatts is maximum allowed, yeah.
And the modulation method is, you're probably going to use, like we've done with the software-defined radio, is use a sub-carrier, where you're sort of literally warbling about at audio frequencies. So just the thoughts that I had was having a look at phase lock loop audio demodulators, which can dig signals out of noise. So just a thought. As I said, I'm no expert on that.
One thing we're looking at is the Domino X, aren't we?
Yeah, looking at other modulation schemes that
Yeah.
have forward error correction, that sort of thing.
Yes. That's an interesting topic is error correction with these sort of devices. Generally, they either work or they don't work. Literally like that. Just in my research, I came across Dave's site, and as a long chat to him, you think, wow, this is clever. What he actually uses, a single sideband communications receiver, and what he's doing is getting the NTX2 and he's just wobbling it about here and using the single sideband receiver, which is narrow band and clever stuff. Found this site as well, UPNet, and they use Hope RF modules for transmitters. I can't imagine they're the best sort of thing. What I thought it might be worth having a look at is there are a number of companies that make bird of prey tracking devices, and they usually use dedicated transmitters, again narrow band type stuff. With crystal oscillators, what you want is spectral purity for other reasons as well. So it might be worth having a bit of research there. And then the other thing, which I'm not an expert, my colleague Richard Hathaway at LPIS was about antennas, but we're going to have a discussion about that afterwards. What I am going to do is I'm going to get some samples to you and things.
Oh, right.
They're ordered up. They come from China. They're on their way. For those that don't know, a Yarding antenna is just a directional antenna, and all it's doing is focusing, instead of being omnidirectional, it's a focused beam device, so absolutely perfect. I imagine there's all sorts of considerations, though, aren't there, about beam angle and being able to find it in the first place and then find it if you've lost it and things.
Well, the balloon, in the case of the balloon, it carries GPS. That's what it's transmitting out. So you'll know
roughly
where
it is.
Yeah.
But in terms of
Only
beam
once you've got the signal.
once you've got it, so I can imagine once you've got it, it's fine.
No, I know it gets better than that because there's the UK Deep Space Network, or whatever it is. It's a bunch of people who track. So if you register the balloon
I
flight,
saw that on one of the
yeah, you may
slides.
register a mission with HubHab or HabHub or whatever it is. Then there's a group of people that will track this.
Yes.
But you've got to be sending out the right signal. You've got to be
That's
on
what
the
Dave Lakeman
frequency
does,
of
doesn't
publish.
it? That's what Dave Lakeman does.
Yeah.
I've tracked some of his
Oh, right.
high flights and things. Yeah.
Right.
Yeah, quite interesting. Quite
Anyway,
interesting.
I'll be eager to find out more about it. I think you also mentioned there was TV, getting TV signals back.
Side scan, slow scan.
Yes, yeah. The place to look is for the radio amateurs and have a look at all the slow scan TV and things. The reason for that is just what? Curiosity as to what's the...
No, I'm basically trying to capture some images. It's cool. Well,
Yeah, I mean, a lot. I mean, we'll talk about the project, but a lot of it is about the pictures rather than just the mission. Because I mean, obviously, a lot of it's for publicity purposes.
Oh, I see, right.
And so, maybe not slow scan TV, but just digital images, basically, just bringing in images back real
Yes,
time.
which are publicity-wise,
Yeah,
it's interesting stuff, isn't it?
obviously there's a lot of recording going on with videos and that sort of thing because they're trying to get the shots of the Earth and the moon
Yes.
and all that sort of thing. But real-time pictures gains interest
Yes,
there and then.
Yes. I mean, there's been some amazing sort of shots and things available.
Yeah.
Right, so that sort of concludes really, and I'm interested to learn more. I think. Right. Are there any sort of questions, or do you want to do, or should we just have an interactive discussion later?
well, perhaps certain
As
points
we go.
will,
As we go along,
as we
yes.
go. And we certainly will have a discussion about antenna because
Yes.
it's an area. I guess most of us are on from the software side and microcontrollers, so the client logic is something we're familiar with. The more you get to the analog and radio side, the more it's magic.
Yes,
So-
that's why I thought it was useful to understand a little bit about this data slicer. I mean, when you buy a module, that's taken care of and things. But certainly there's just much cleverer ways of using that power and getting those signals across those distances and things. Okay, so
Thanks. Okay, next up. Back, forward, laser.
I gotta go, but thanks very much for organising this.
Do you have a number for Milano?
I use Just Eat, but I'm sure Google knows.
Just need, okay.
They're great, yeah. Primo Veggie, that's my favorite. And then make sure you click on, if you go on Just Eat, make sure you click on the deal for the 18-inch pizza for £12.
You sure don't want to stay for 5 minutes? I've managed to squeeze trains into this.
I'd love to, but I've got to take... You know what I'm doing for the... Listen, I want to get automatic bank feeds from HSBC to the Zero thing.
That's more important than trains.
And
Absolutely. Well, that's debatable, but we'll look at it.
I have to go and I have to send a document through the friggin' mail.
Paper.
Paper. That's what I've been farting around with for the last... That's what I've been...
Learn lots. See you later. We had a bit of an argument in car as to how to pronounce telemetry. Telemetry? Telemetry. Right, okay, so glad we covered that one off. Okay, so dictionary definition of telemetry. Telemetry. Oh, see what you've started.
All the way here we've had this.
Is that it's a highly automated communications process by which measurements are made and other data are collected at remote or inaccessible points and transmitted to receiving equipment for monitoring. So a lot of you might not be aware, but RLab, very early on, in the very early days of RLab, we built a RF-based system for capturing images of wildlife for ZSL. So what we've got here is just a quick example of, we've got some RF radios, a camera, proximity sensor, and this is sort of how it developed: 3D printed cases, enclosures. We started off with XPs, we moved over to Sisico radios. We started off looking at mesh networks and found that when we moved over to Sisico, it didn't support mesh networks, so what we were looking at was long-range peer-to-peer Arduino to Raspberry Pi to Iridium. So these RF images were very low resolution, sent over RF radio, and then sent over the Iridium network back to London Zoo, so that these cameras could be put in very remote locations and capture images of wildlife. So that was that. So really not a lot more to say about that apart from
So
that.
why did you switch from XB to the other ones? I can't really recall.
This was very early on in XB life, and it was difficult to get them working out of the box. Just by the off chance, we ordered some products from Sisico, which were enabled us to work off with a low power Arduino solution out of the box. You didn't have to build anything, and they sent a couple of their radios, and they had hardware ACK built in, so we didn't have to do anything on the software side. That later proved not to actually be true, especially when you have multiple of these. So Barnaby actually done a lot of work on time slicing and making sure that the messages weren't overlapping as they were sending, and built a whole architecture and a nice little solution, which you've probably seen at a couple of maker fairs that we've shown off. So yeah, it wasn't the ideal solution. We lost our mesh network, but it was still quite a good solution. From the base station, we could cover on the books 12 kilometres, so we could have several cameras 12 kilometres away from a base station, and one Iridium modem that sat there and sent images when it was not so busy. Probably not a very cost-effective solution. Iridium data is quite expensive, but it worked very well for London Zoo, and they went on to actually win a £500,000 prize from Google to continue this work. Yeah, just an example of how we've already been involved in a project like this, but this was on the floor, not going up. So that was one.
So what's the actual cost of Iridium then, in terms of upfront cost and usage costs?
Well, we've just been doing some plain temperature data, and basically for another project we worked on the buoy that you've seen, and I think that works out at, is it £1.20 for 256 bytes? 256k, sorry.
No, it is literally, we were sending, we reckon we could afford to send 50 bytes a day, and it was going to cost us £1 a week or something.
Oh, sorry.
That would work
The ZSL
anywhere on
project
the
was
planet.
free, so we were...
Yeah, from anywhere on the planet, but 50 bytes isn't much.
Yeah. Yeah, images even at very low resolution, we were catching them on an SD card at 640 by 480 and sending a thumbnail, and it was still working out. In fact, I think it was £4 a picture. I think.
How does that compare with using, I don't know, cellular phone?
And the trouble is, these are going in remote places where you have no GSM,
Yes,
so
I mean,
literally
it's much more
Antarctica and places like that. So yeah, that's one of the examples. And the other example we use is with trains. Recently, you probably know Barnaby and I have been obsessed by trains. Though not really applicable for your users on this particular project, but BLE is Bluetooth low energy. It's incredibly low power. It's compatible with a number of modern devices like your phone, your iPad, your anything with a USB dongle. Works out of the box, no pairing required. A lot of Kickstarters coming from or growing from here. You've got no product certifications required. For example, Apple, our favourite vendor here between a lot of people, they require certification for Bluetooth devices unless it's a BLE device, in which case they're happy to watch a YouTube movie to see that it works, and then they're certified. So their long review chain is actually quite easy to get through now. People are going mad about the Internet of Things, but I've got a new acronym which is CTMT, which is close to me. Something I can't remember. I made it up and forgot it. But basically, a lot of people are obsessed with media at the moment about the Internet of Things, and really, what's the point in having things working remotely when you're not there? When really it's probably better if they work and send you messages when you're close to them. For example, if your plant needs watering, having a message over the internet when you're driving your car isn't particularly useful. If it knows that you walked into your house and that your plant needs watering, and the same when the washing is done, get a little ping on your message, starting it off while you're in the house. Do you really want to start a washing machine over the internet unless you've got a IoT leak detector as well? That's probably not really a great thing.
What you're talking about there is the combination of remote monitoring
Yes.
and remote command. So the opposite of the telemetry is telecommand. And what this is, it's very short range.
Yes.
Telemetry command.
I mean, basically, just covering off the fact that there are different ways of communicating over air and sending data. This is a new up and coming, not relevant to this particular project, but an interesting project that we've actually worked on in the space.
Well, it could be for the same reason that you went with a hybrid solution for the zoo project. That you're going to use one type of radio for sensors to a hub, and another type of link. Then, I mean, you could have a hub separate from a Pi, and then the Pi running your Iridium.
Absolutely. I mean,
so the thing there is that you're dealing a lot more with wireless connections.
Yeah, the point there is that both of these systems work over air, and they've been done in Hackspace. That's what we're covering up here. But
what sort of range do you get on that?
Interesting range.
Quite far.
But much less than the BLA.
But much less than obviously your RF radios.
I mean, the main finding from the RF radios were that the fully digital systems, which do it all for you, like your XPs, are usually more trouble than you're worth. If you're trying to push them to the limit of range and of data rates, you have to end up second guessing the way that they're buffering things, the way that they're constructing packets. One of the big issues we had was that because we were trying to get several radios to talk at once, we had to know how big the packets were, and they wouldn't even tell you that in the data sheets. It was just a right pain. So, as you were saying, working with the digital transmitters and receivers I think is the way to go. You have to understand down to that level. Whereas with something like BLE, we found that does work really, really well, that the extra complexity of that protocol does mean that what you send gets there, and it sorts out multiple things talking and stuff really well. But you haven't got anywhere like the range, and these are using comparable powers and comparable frequencies.
What sort of range? I mean, just
we've only
tens
had
of metres or hundreds?
up to 100 maybe.
Up to 100 metres, yeah.
That's the sort of thing we've got off BLE.
What frequency band is it?
That's 2.4 gig.
Okay.
All of the stuff we've done is at 2.4 gig.
Which is not the best frequency.
No, not for the best
And
frequency.
sort of our feelings about it are that the ISM bands, the UHF bands, will probably be used for sensors to a hub and things within commercial buildings and domestic buildings. Zigbee, but I'm just fascinated. But I haven't played with
They're very cheap.
So, I mean,
BLE.
the real
these are going to
selling
be.
point for BLE is the fact that it talks to your phone, which is so useful in
Yes.
so many applications.
yes, but tens of meters,
Definitely 10.
tens of meters, right?
And they can normally tell how far away you are as well, which is there's good proximity detection on them as well. So it makes
How
the
do they
use
do that?
cases very
Like-
well.
Signal
what's it called?
strength?
Time of flight?
No, they're about signal strength.
RSSI.
Yeah.
So yeah, just
Wow.
a couple of interesting things that we've done here that fly over the air, not up in the air.
So we've done land and sea, we're just about to do air.
Yes, well we've had absolutely we've had the sea one as well, and that went up with the Iridium satellite. So yeah, land, sea. Now we've got to conquer the air. So I don't know who's talking next. Oh, here we go. Yeah, land, space. So, yeah, hopefully we'll conquer the world at some point.
Once we can put our own satellites up, we've got enough lasers that it should be quite simple.
Oh, I don't need that one. That's the example of the hoax that
Yes,
you were
yes.
talking about. And one of the other problems with it is it's not 2.54 millimetre pitch, so you have to do weird contortions.
Oh, I was wondering what that was.
This is why. I don't know where they've gone, but I haven't got headers on.
Oh, I see. Yeah. Mhm.
Got a 2 mil.
But that was the XB standard, wasn't it? Which
Not XP's one
Why
though.
do people go non-standard?
There we
to
go.
get the number of pins. I think it's more.
Okay, so that's the sort of general view, and then this now is about the Hack project, the high altitude balloon project. So Richard will do an intro to the project, why we're involved, what the kind of things we're doing. Then I'll go over some of the components and hopefully get a demo going. And that's with the NTX2 Radiometrics radio off of a small Arduino, acting as a beacon, and then receive that on an SDR setup. And then Richard's done some design work on a flight computer to go with go in a balloon. And he's got a prototype board at the moment, and so he'll present on what the design of that is. Last week, Telegraph, so we're looking to go about 30,000 metres. A primary school in St Albans got to 120,000
That was Dave
metres.
Aikman though, wasn't
Yeah,
it?
and the bear survived.
Yeah.
Right. Let's do yours.
Yeah.
Bring my pole.
Yeah. No, so that's back, forward, laser.
Right.
Okay.
Okay. Alfonso. Titled the Mattel Hab project. The real driver of this is RS components. We're trying to bring it all together. So the guy from RS Components, Pete Woods, is the overall project manager, and he's been working with Mattel, who are bringing out this new toy, and there is a film coming out later this year, Superman film. So they want to do very much. I mean, it's been done before, but they just want to get him up into space with a balloon, take lots of photographs, obviously of him plummeting to Earth.
Flying through space.
Sorry?
Flying through space, not plummeting.
Well, we will get photos of plummeting to Earth. Whether if we can then doctor them to make it look like flying, then yeah, that would be a significant advantage. But very much, it's not just about doing it; it's about the visibility of the project. So RS are looking to get blogs and to get people involved in visiting their Design Spark website, and they're very keen for us to tell how we've done it and what we've been doing.
And which RS components we've used.
Yes.
or not?
Yeah, and unfortunately, probably the two key components, the GPS and the transmitter, they don't stock. But everything else they do.
I'd just say that it's probably remarkable timing that on Hacker Day they release an autonomous balloon popping quadcopter this morning. It might have some kryptonite on it.
Why are we doing this, and why are we asking people to join us? It's well within our capabilities. This is something that has been done before by primary school kids. Probably a bit like building IKEA furniture. That if kids can do it with it, probably we can. I mean, not certain, but we can drop heavy objects from a great height. The objects are actually getting heavier and heavier. But we started off with just the figure, but now we're looking at capsules and cameras and all sorts of things. So we could be certainly over a kilogram of weight to drop.
Becoming lethal.
Well, we thought it was interesting to get involved. Although it is proven technology, then obviously if we can get involved with this project, then we're going to learn a lot that we can then leverage for Matt's balloon projects, or Tom is looking at some balloon projects as well. So we think it's something that's worth getting involved with. One of the things, the teaming relationships is quite interesting, because the RS, for instance, are trying to work out how they address this market of makers and how they get involved with that. They see something's happening, but they're interested in exploring how they can link together with Hackspaces and makers generally. With their design spark, they're looking more at trying to build a community or work with that community rather than just ship out boxes of components. We're doing, as a Hackspace, we're doing this also, with things like within the community and with local businesses. We're trying to understand just how we can support overall innovation through hobby through to commercial, and we think this is a good project to do that. Publicity, obviously, we will gain some visibility out of it, good or bad. And finally, it's fun. We get to play with balloons and go out in the middle of fields and
Drop things.
I broke it. Sorry.
Is it infrared or wireless?
There you go.
Right, well, we had the opportunity to put together a #1 winning team for this project. Unfortunately, we missed that opportunity, so this is what we've got instead. Obviously, Mattel have provided the figure, so they're
good at them.
They have a long history here of, you'll see Mattel also do the Barbie, which, and if you look right at the top here, it says in collaboration with NASA. So luckily Mattel bring to us a level of credibility and experience in the space race.
What did NASA have to contribute to Barbie?
Sorry?
What did NASA have to contribute to Barbie?
Well, probably the spacesuit, I would have thought, yeah. David refers to RS as radio spares, which I think is rather cute. A long history of being in the market. Very interesting. When radio spares started up, they would not supply amateurs. I mean, they would only supply businesses. You had to be a registered business. So it's rather interesting now that they've sort of taken this other approach where they're coming to places like us, and they will actually supply to the general public. Jude Pullen has been brought in by RS as well. Jude is an amazing guy at putting together all sorts of structures. He's been working on the capsule with, and Alex will do some 3D printing for the capsule as well. But Jude worked for Dyson. He now works for Subaru. But he's just a total innovator. He can build anything out of cardboard, including banana suits. Obviously, here we have the opportunity with RLab. RLab said they could build us a spaceship. Or, well, we thought they said they could build us a spaceship, but in fact they said they had space for a ship. Or had no space left after the ship. The boat has now sailed, but the motley crew is there. Dave Ackerman obviously is the experienced guy here. He's a balloon obsessive, and just I think he's launching balloons most weekends, and is acknowledged to be one of the in the UK certainly one of the.
So looking at his colleague, does this mean we're going to get weird in-flight catering?
A bit worried. Yeah, he does have some strange friends. Yes.
Potato, yes.
But I thought the bacon was quite good. Ryan has the web address Bacon Wave, and he's into bacon. Ryan is into bacon very heavily. So.
How does Heston? Is it?
It was a
It was
TV
a
program.
TV thing, yeah.
They
launched a potato.
Oh, the
They did
potato!
a
I missed that.
potato,
Yeah,
yes.
that did nothing.
So,
It wasn't up there long enough to do anything.
He's still got it in a sealed tube, hasn't
yes,
he?
yes, he's
on his
done.
desk.
He did the Raspberry Pi.
Babbage Bear.
Yeah, Babbage Bear and that sort of stuff. So, yeah, he's.
So the reason I refer to it as radio space, I used to work for STL, and STC owned radio space. But they wouldn't sell any bloody components to me though, even though I was an employee.
So if you did work for a company who they supplied, you could just order all these numbers, and the company never knew what you were ordering, so you could get all sorts of things for yourself.
Yeah.
Not behaving.
Yeah. So overall on the how we're doing it, I mean, just a note on the picture there. That is a picture that Dave took. There's a number of pictures on his website, and that's the balloon actually bursting.
Wow.
So he put a camera.
That must have been pretty lucky. We got
They're frames on the video. There's like 3 or 4 frames, consecutive frames, and obviously because it's in space as well.
Wow.
And you can actually, so he had one of the cameras was pointing up, looking at the balloon. He had multiple cameras, and so this is looking up at the balloon, and you can see there's a very faint cloud in the middle, which he thinks is the talc that was actually in the latex of the balloon as it actually burst. Because I mean, obviously this is at high altitude, very very low pressure.
Did that burst due to altitude, or was it a
control?
Yeah, that was altitude.
He doesn't trigger them.
No, okay.
So yeah, I mean, it's about 3 or 4 frames of a thing just as integrating, really good. So for our mission, we're looking to go get everything done before September, which is because of the film and also Christmas, because they want to sell toys for Christmas, so they want to sell these dolls, figures, maybe I should say, before Christmas. So somewhere, the actual site where we will launch from obviously will just depend on, it may be a site that David has down in West Country somewhere.
Yeah, I can't remember where it is.
And hopefully, I mean, we're not trying to do a long distance here. So, I mean, a number of these balloons, they do, you know, are launched for the purposes of going long distances.
This will be what, 3-4 hours, I think.
Yeah, I mean, we're looking for a total flight duration of about 4 hours.
An afternoon, we can cope with that.
Yeah, and the recovery obviously then should be in the UK.
The launch site. When you're going to loft one of these, you have to get permission. Well, actually, it's.
Is it a NOTAM?
No, that's part of it. There's
okay.
a NOTAM, but you basically get permission to break a rule. I can't remember what it's called, an exception. That's it. But it takes 28 days, the whole process. And there are some sites that have effectively fixed
So
exclusion
if you
from
launch from this
the rule.
particular location, you don't need to.
Yeah, so there are two in Cambridge, and I think Dave has got his gardeners or a field out the back or something.
There's one he talks about on his website in Berkshire, so I don't know where that is.
He used to live, I think, Newbury way. I think
Right.
I don't think he launches from Newbury anymore.
He's northwest Bristol.
We're looking at a number of flights with different payloads. As I said, a lot of this is about getting pictures of the figure coming. So obviously, just to have the figure taking a video is not going to be much use because it could be anything. So we're looking for pictures which have both the character and obviously in space. So curvature of the Earth type figures, horizon type pictures.
The Superman in front of it.
Yeah, so although the figure, so we will want to get a photograph and video of the figure leaving the capsule or leaving the balloon. Then we also considering so there will be a capsule that we will need to create, and will probably give us the best pictures, but very of the Earth and the horizon and that sort of thing.
Are you showing this later?
Yeah, well I can. I mean obviously that's one of the cameras that RS. Again, the cameras that David normally uses are the GoPros, I think, which are smaller than that.
The size of that.
RS don't do the GoPro, so that's the other thing. So they're looking at this Panasonic camera, which is
it's very heavy.
Chunky bit,
That
yeah.
camera is 4K, where the GoPros, I don't think they do the 4K GoPro.
yeah, I think that is 4K. So it
Does have some very stylish accessories.
sorry?
What, the GoPro? Oh, that, yeah.
Yeah.
Very stylish.
So, yeah, so we're looking to have a capsule which will have cameras in. They either the Panasonic or the GoPro or maybe Raspberry Pi cameras. That's the other alternative.
They are nice and light, aren't they? It's an advantage, isn't it?
The
Raspberry Pi camera.
yes. So and I know David has used those quite a lot in the past.
But you do need multiple cameras.
Yeah, I mean, even with something like that, the battery life could be an issue, so we may have to put an external battery on it. And it's really the cameras that are going to make the payload quite heavy.
What's the total maximum payload you can?
I think you're allowed up to 2 kilos, but that's quite. I mean, obviously, the heavier you go, the more hydrogen you're going to put into the balloon, and
the bigger parachute you need to get it back down again.
yeah. So I think they're using a 2 kilo capable balloon, but we're trying to work around the under a kilo. I mean, obviously, also the heavier the payload, the more risk there is of when it lands and hitting something and damaging something. And,
Yeah, if we have to buy a new church roof because we've landed a thing through it, that might be
yeah.
Yeah, also the paper headline of Man Killed by Superman.
Well, I suppose any publicity is good publicity.
It's like a strange Hackspace member
I think
caught
it's
saying,
right, yeah. Why not chance?
Yes, that's right. Yeah, we're looking at some sort of camera wing as well, so as he's plummeting to Earth, that we can actually get some pictures of both the figure and the Earth rushing towards him. So in terms of our involvement, I mean, we're involved with the tracking mainly for recovery. We're not going to, if we can get some real-time pictures, it's good, but most of the video will be recorded, so we need to recover that. Obviously the cameras are quite expensive, so it's not so important to get the figure back, but from a value perspective, but it's probably important to get it back, because to say you've done it, basically, just, and they do.
Is Superman going to fly, or is he just going to plummet?
Well, this is one of the challenges.
The subject of heated.
Oh, see,
yeah.
Oh, right.
The actual storyboard part of it we're trying to keep out of, because there's a lot of experts on Superman out there, and if we would rather get involved in the technology bit rather than the storyline. Originally we were going to use a different character, a Max Steel character that they had, but then because they were launching this new model, then they wanted to do Superman. I mean, Superman is not ideal for this, because he doesn't need a balloon, he doesn't need a parachute. I mean, the whole thing is bizarre in that sense.
I was thinking you could make him guided, couldn't he? So he could,
yeah, I think the sort of
he's got to tumble through the sky.
well, I think if we can do the wing in a way, and this is more Matt's and Alex's design of the parachute and this sort of camera wing. So basically, if it is possible to hold him and have the camera wing or something, so we can actually see him, and then the parachute. That would be ideal. But I mean, it's uncharted.
I would have thought it'd be easy just to record a video of something falling down and then superimpose them on our.
Well, yes, I mean, it would be very easy to do that.
Green screen.
I mean, we could have done that
Until you
already.
found out.
It saved us a lot of problems, because I mean, we've already got those videos. We can blue screen him and just stick
You
him
could do
on.
the same as you did with Babbage Bear, which is to shoot him sort of launching from the balloon or something like that.
Yeah, the capsule will have cameras, so you'll see that. But that's only like a few frames, and there are we'll talk about stability issues, because when he is pushed, you're talking about there's not much air pressure up there, so there's not so things get tangled up. There's, as he's ejected from the capsule, there'll be a reaction force. There's all sorts of issues, and we will have multiple attempts at doing this, but it's going to be an interesting challenge, for a mechanical challenge, if you like, as to how we can effectively get him looking right. No. I don't think some of the design challenges, as we're saying, temperature is an interesting one. The environment, the temperature at that altitude is down to -40 degrees. Although we may have overheating problems, because the actual devices tend to get quite hot in themselves, and of course you haven't got the normal convection, and you haven't got the normal sort of cooling type thing. It will be in a probably a polystyrene, or what we're hoping is a 3D printed structure to reduce the temperature drift, but also to make it softer on impact. So we're looking at very low density 3D printed enclosures for the devices. Yeah, so and the pressure, then at that altitude you're down to about as low as thousandths of atmospheric pressure. So we have to consider that for things like batteries and sealed devices and that sort of thing. So, and also the lack of air, as I said, has an impact on cooling, conductivity, and also the physical dynamics of how things work without any sort of friction in the air. We're 40 kilometres up, so from a radio perspective, that's quite a long way. I mean, in distance, hopefully we can keep fairly close, but the radios, they have run these radios, I think 800 kilometres is about the limit that they've actually managed to
What was the
a proper amateur receiver.
Multiple receivers as well.
Multiple receivers. But I think they have. They have the advantage of multiple receivers, but I think on a single operation they have actually picked up the fluid, over a distance. So they can track.
Is that a linear distance of 8 kilometres?
That's fine. Well,
how much up and how much down?
well, I don't think it matters much about that. If you're 800 kilometres, it probably doesn't make a lot of difference.
It's still impressive that some of the what
Yes.
transmitter.
Yes. The other thing that we were looking at is if you look at some of the videos that have been taken already, then lighting can be a problem with that light as well, because you've got direct sunlight, so chances are that some of your shots will either be very much in shadow or the camera can be pointing at the sun, so you've got to be very careful as to the orientation and how you do the lighting. The lighting is nowhere, not as diffuse as it is down at ground level. So we'll probably need multiple cameras and maybe multiple launches to actually get good shots of the lighting. Stability of the payload is interesting. If we've got a wing and a character and a parachute, just how we bring those together. Obviously there is wind up there and low ground, as I said. Safety issues, potentially a 2 kilogram payload, as I say, although we hope to get down to a kilo. Balloon will be hydrogen, so we need to consider that. Use of helium now is sort of frowned upon because of there's not much of it left. It's scarce and expensive, so it's typically now to use hydrogen instead. Power supplies, obviously the batteries we use will have to be good at low temperatures. We tend to use lithium primary cells, which are good at those temperatures. Certainly for the time that we're going to be flying, we're thinking about for the actual flight time, about 4 hours, and then there's recovery time. So we're looking overall about 20 hours of operation, which is, for a lithium primary is absolutely fine. So the regulations we have to fit in with the CAA, has already been mentioned. There is normally a NOTAM notification manual, and also you need specific permission within it. It can take 28 days. I mean, often it happens a lot quicker. I mean, the NOTAMs we've had here for the laser shows, we've typically got within 7 days or something like that. So they typically move faster. And
I guess it depends where you're going to be off. If it's over in Cambridge or Bristol, you're probably.
Well, if it's there, I think they've got it anyway. But I think that
You're doing it in quite a lot of Heathrow.
Right.
If we're in quite a lot of Heathrow at this point, so maybe they might have to more.
the radios, I mean, there are regulations with Oftel around the radios. The only radio, it's doesn't help here being, if you're a radio ham, it doesn't actually help you because radio amateurs aren't allowed to do any more than anybody else when it comes to balloons because they're unattended and they're airborne. The only bands that can be used for airborne are 2.4 and the 434, and power is limited to 10 milliwatts. I think also you're not allowed any gain on the antenna either. So yeah, you couldn't do it anyway. Yeah, so as long as you meet those regulations are okay. There are regulations around the GPS as well, and that does affect the choice of the GPS that we've used. A lot of the there's within the if you make GPS receivers, then so that they can't be used in missiles, there's a limit on the height of both height and speed. So a lot of them are artificially limited as to the height they can go. It's very much down to interpretation, whether it's height, when it says height and speed, whether it's a combination of both. So some manufacturers will limit on both on height or speed, and some will do it on height and speed. So we have to pick a GPS that is limited, not limited by height. A surprising number of the commercial ones are limited to, I think, 10 kilometres. So when because obviously they measure the altitude as well. When they get to 10 kilometres, they just don't give you the data. So the answer being by from China. Sorry? The answer being by from China. Well, no, the U-Blocks ones. I say it's entirely a question of interpretation. So the U-Blocks require both. I mean, it may be interesting if you start looking at rocketry, whether we can go fast enough to. Yeah, when we are building a missile, maybe we can test it. Yeah.
So how can some people sell them without? How can some people sell them without the limitation?
Because it's the interpretation of whether it's. I mean,
it's the policing or enforcement. So if there's no real enforcement, then
if no one complains and no one investigates, it's not a problem.
But they've interpreted it that it's got to go very, very fast and be very, very high. Whereas other people interpret it as, it's high or it's going fast. Yeah. So this is just down to their interpretation.
There's some issues also if you're using mobile phone technology, you can't do it in certain circumstances. Does that mean have alternatives to sending data?
Well, you're speed limited with the mobile phones anyway. The mobile phone networks were
getting on the road.
Yes, were designed for high-speed trains. That was the target, but they happened to work to an extent with aircraft. You'd be surprised how quick the balloon can move up at 50 kilometres.
Use different base stations than
but I think David said they have done stuff with mobile phones and GSM modules and that sort of thing, but they only really use them for tracking on the ground. They're only effective up to a certain altitude. They won't work with the altitudes that we're looking for.
When it's come back down, is it a field with there, and we can no longer track it because it's not the line of sight.
That's right.
And which is mobile phone might be useful. But if we can afford the extra weight.
They don't. I mean, he doesn't seem to use them very much at all.
Does Superman use Apple or Android?
I don't know. Ask Warner.
Since he's corporate, it'd probably be BlackBerry.
Very good point.
Okay, that's it. Why don't we take a short break?
Yeah.
And we'll cover off the rest. Quick 5 minutes.
Switch SD cards.
Instructions on it?